Hello, I'm Sue Nelson and welcome to the Create the Future podcast, brought to you by the Queen Elizabeth Prize for Engineering. Can you guess what this sound is? It's simulated Martian sand bouncing off the wheels of a Mars rover. I didn't say it was going to be easy. I'll be walking on Mars with Airbus engineer Abbie Hutty a little later on. But since it's the 50th anniversary year of the first human footsteps on the lunar surface, this episode is going to start with the moon and a personal view of some of the engineering highlights behind one of the world's most iconic moments.
It's one small step for man, one giant leap for mankind.
Neil Armstrong making history in 1969. And this is how Lord Brown, engineer and chairman of the Queen Elizabeth Prize for Engineering Foundation, views the success of the Apollo project.
It's an outrageous idea to take a human and put them in another world. It was a challenge which had not been met, with a finite timescale to get there, with the resources needed, and attracting the best people from all walks of life, because they said, we can do something which is different. We need to do more of that. But in the end, it's setting that challenge and time.
My first guest is an engineer who worked on the Apollo program and has enjoyed a career since then that has spanned the space shuttle, writing books, and continues with his current position as editor of Spaceflight magazine. David Baker, welcome to Create the Future.
Thank you very much indeed.
What were you doing when Neil Armstrong first set foot on the moon?
Well, I was very closely involved in looking at the data that was coming in Building 31, outside Mission Control, the familiar location for TV audiences watching this dramatic event. And there was a whole series of us, or a range of us, in a series of different departments surrounding Mission Control, which were looking at the data as it was coming in. And my particular job was to see if any funnies were coming in that we were seeing.
Funnies?
Yes, funnies of data, things that were not going as well as they should do. And we had this template that we'd written that could propagate on for later missions. But, of course, with the Apollo 11 mission, this was the first time that we were taking the LEM, the lunar module, right down to the surface of the moon. So we had to monitor to see if there were any conditions that we were encountering which would alter dramatically the sort of flight profiles for landing we were planning for the next missions.
So you're in Houston. You are looking out for funnies.
That's right.
How did you get, because obviously you're British.
Yes.
How did you get from living in Britain to suddenly being there when history was being made?
Well, obviously the bottom of the barrel was being scraped horrendously, because I was fortunate in receiving a scholarship through the school that I attended in Hertfordshire, which was connected to a number of American universities. And there was a NATO program at the time, which was the inspiration of Senator Clinton Anderson, who was the senior senator of New Mexico and was very, very pro-space, and in fact was presiding over a state which had a lot of research on nuclear propulsion for upper stages of rockets. And because this was an intense period of the Cold War, opportunities existed among all NATO countries for schools and universities as well to put up potential candidates to go and work on these various programs. And for me, it was the ultimate go-to job.
Of course, of course. And what aspect of it were you most interested when you saw that launch? Did you witness the launch from the inside of the control room, or because obviously you weren't at Cape Canaveral?
No, I wasn't. I saw it like several million other people on television. But it was very interesting that we were, what I like to say, we were cerebrally immersed in it with the data that was flowing through. And in that pre-digital age and a time of pretty scratchy television, it was actually the natural human emotion to want to look at the screen and see what was actually going on. But the real information was streaming down through all the data channels, and really my work began at the start of the countdown, because we were looking right the way through to see if there was something in there that we would need to alter for later missions.
So what data were you specifically interested in?
My own particular responsibility was looking at the performance of the command and service modules and of the lunar module. We were concerned that if there were any delays in prosecuting various actions, if, for instance, separation of the lunar module preceded, in lunar orbit, preceded some particular problem with the command module, because the lunar module was the only way of getting back home if there was a problem with the main Apollo mothership. And
so lives were at risk,
lives were at risk. Very, very much so indeed. And I guess it's counterintuitive to reflect that the attitude we have was not that this was the culmination and after it would be job done. It was essentially the last of the development flights, we thought, Apollo 11, because this was the final piece of the jigsaw going right down to the surface and conducting operations on the moon and coming back up. So we needed to know that all of those steps and procedures were fine for building upon to keep the crew longer on later missions.
How did it feel at the time for you? Because without being rude, you must have been quite young.
Oh, I was very, very young indeed. Well, I went in my late teens, and by my early 20s, I think I was quite involved in the Gemini program that preceded Apollo. I felt, quite frankly, in general terms, I felt the opportunities in the United States then were far greater than they were in the UK. We were just emerging from a period of real intense austerity, of rationing. There were limitations on government work in aerospace projects, on the inertia from developments in the Second World War. By the early 1950s, Britain was actually ahead of the United States in a number of aircraft performance capabilities, and that in fact inspired people like me as a child, as a boy growing up. And then it all began to grind to a halt when I reached my later teens, and I was actually supposed to have become a pilot, an airline pilot, but I had a problem with my ears, which later cleared up, and fortunately I took the opportunity to go to the United States. But my feeling there was very much the case that here everything was on a constant level. There were not the ivory towers that existed in this country in the 1950s. I loved that. I loved the fact that you could rub shoulders with test pilots, with astronauts, that you were all treated as equal and members of a team. And I think one of the greatest motivational lessons I learned was that not to achieve self-pride or self-fulfillment, but the fact that you were not the weakest link in the chain, and that you would let your team members down if you didn't brace up, shape up. And there was that pseudo-military approach toward a sense of responsibility, and we were all doing it for a cause we all believed in, and we were just, nascent rocketeers in the making, and it was just so absolutely thrilling.
I can imagine. For you as an engineer, looking back on Apollo, what do you think was the greatest challenge, bearing in mind that there were so many of them, technical engineering challenges, to get man on the moon by the end of the decade, which JFK famously threw down the challenge? Yes.
Well, there have been many people who have spoken about the enormous technical and direct engineering challenges to invent so many things that were needed to do a job, the prosecution of which was still a big unknown as to how we were going to do this job when the president laid down the gauntlet like this. But in looking back, I think that one of the most important enabling influences was the way the whole management structure came together after 1963. I pitched right in at the beginning on the cusp of a massive transformation in NASA, which had been originally a metamorphosis from the National Advisory Committee for Aeronautics that had essentially been a lot of scientists and test engineers who had done research development work to put American aviation companies in the foreground of world achievements, looking at aerofoils, looking at aerodynamics, flight control systems. Here was an organisation suddenly that had to manage operational activities as well as build and contract out for hardware that was designed in-house. They'd never done that before. And so for 2.5 years after the Kennedy challenge, it was devolving further and further into an unholy mess, and we would never have been on the moon had there not been a massive transformation in bringing in the engineering examples of Bernard Schriever, who had pioneered in the Second World War systems engineering as a concept. The Germans brought their methods from Europe. Von Braun was still the architect of the V2 and the brains behind the Saturn launch vehicles. He still brought the waterfall chart method of looking at project management. And it couldn't encompass the vast array of, as we matured, 20,000 companies and 350,000 people working for a common goal. So a new concept was needed, and it was essentially from the Manhattan Project on through to the big development projects for ICBMs and big missiles in the 1950s that Bernard Schriever applied World War II systems engineering methods to the missile programs, and NASA realized, very senior management, Jim Webb, the NASA administrator, that we needed that in NASA. And so suddenly there was a transformation. And that, I think, while it's probably a boring answer.
No, it's interesting, actually, because that's what engineering is also
Yes.
about. It's not just providing the solutions.
Yes.
It's putting the framework in place so that
Yes.
you get the best
Yes.
of
Yes.
all your component
Yes.
parts as
Yes.
well, isn't it? It's
Yes.
a lot of project management effectively too.
Yes. And I think two messages went out when George Miller came in as head of manned spaceflight operations in 1963 and really shook the whole establishment right up and tipped it on its head and rewrote the rule book. He brought what are now known as the GEM boxes, George E. Miller, GEM boxes, which were the beginning of a series of adaptations of a US Navy program called PERT, Program Evaluation and Review Technique.
Great. PERT. Yeah.
PERT by name, and well, there you go. And
Thank you very much.
And so it essentially created an environment in which we could all embrace the war footing, not in combative or necessarily military terms, but most of the people that I was rubbing shoulders with, and I have to admit that I subscribed to, we were very committed to championing the ideological cause, it sounds terribly cheesy now, of what we defined as democracy and freedom against what we perceived to be a totalitarian autocracy that was essentially threatening the world order. And in our naivety back in those days, I say naivety because I think it was not as simple as we assumed at the time.
It's for the greater good, effectively.
For the greater good, that here was a society that did not want the strictures of an extreme Stalin-esque societal structure being imposed upon free-thinking people, and that was what drove us a lot, and it's one of the most important aspects of Apollo people.
How did engineers pull it off, though, when it's often been cited that they were using technology that had less computing power than a modern smartphone? Was it purely ingenuity based on existing technology, or was there any sort of leap forward in a specific aspect of the technology that was required?
Innovation is the child of challenge, and the challenge we faced required innovation, discovery, invention in order to make it happen. And I think a word about that particular aspect, computers, it is often said that the computing power, the processing power, the capabilities of the Apollo guidance computer, which was one in the mothership, the Apollo, and another one in the lunar module, identical. That in fact they were being capable today of powering digital wristwatch, for instance. But in fact, the important thing to remember is that they were not controlling all of the mission operations and all of the computational activities. That was buried in the serried ranks of freezer-sized computers down in the real-time computer complex, the RTCC, on the ground, because one of the things that was decided wisely very early on by Dr. Charles Stark Draper, who had the responsibility for all the guidance and navigation systems in the program, was that you're not going to be able to delegate to the crew total command authority on navigation, guidance and control of the spacecraft. You're going to have to base it on the ground and find a means of having all that information transmitted to the crew in very, very small batches that in those days had to be written down by the astronauts using a pencil and paper and pen, and then input to various computer programs for just the next set of activities. So the mission wasn't run from the spacecraft, and it wasn't run from the computers that were actually on board. It was just the processing programs for the next 7 steps. And even in the landing, we had 3 separate computer programs just to handle the landing. So you'd switch from one to the second to the third.
Well, I was going to wait until the end of the podcast to put some questions to you from people on Twitter, but I'm going to bring this one in now because it relates to exactly what you've just been saying. It's from Dawn Baisley. How did you do your calculations? Slide rule, room-sized computer, human computer, or all 3?
All 3. There was an awful lot of mental work going on in terms of, I think in those days slide rules were essential. And, you know, I was at Annapolis a few years ago, and apparently the US Navy still requires its pilots to learn how to operate slide rules. And there was an astronaut who only made it back to his carrier when all the onboard displays in a very, very modern combat fighter just a few years ago completely went out, and he had to find the carrier and had to work out how much fuel was on board to adjust the throttle settings to get back, only because he carried a slide rule in his flight suit. And I think the US Navy must be still the only armed service operating any kind of mechanical device that currently still uses slide rules. The slide rules were essential and were used on board as well as on the ground.
Got to remember, of course, I mean, I have no idea how to use a slide rule. I suspect many people listening have never seen a slide rule either, so that's something to Google to use modern pilots. Now, how did you end up working on the space shuttle? What were you doing there? What was your job? Obviously, this is quite a bit later, but
yes.
Moved on.
Yeah. Well, after the initial Apollo landings, once the dream had evaporated that we were going to be essentially installing a permanent human presence on the moon, the next project, which really was the focus for NASA in being able to try to reduce the cost of spaceflight, didn't quite work. The shuttle had already been determined to be the next program for NASA even before Apollo 11 landed on the lunar surface. And I was very much of the view that no matter what we dreamed up and what we put down on plans and what we commissioned in terms of studies, nothing was going to happen unless we got it past the legislators and the bean counters, the people in Washington, essentially, in the Beltway, who controlled the destiny of not only NASA but many space operations in the United States, the military as well. And I chose an opportunity to go up to Washington in order to support NASA's bid for budgets in various congressional hearings on the Hill, and so became very involved in the development of the shuttle and had to step aside from NASA for a while because I was employed by the Department of Transportation to do an analysis of the econometrics of the shuttle. So I became quite familiar with all of the economics studies, and there was one particular company that was responsible for doing the economic analysis on the shuttle. And I worked in Washington, lived in Georgetown, and then from there went around the world representing NASA to recruit organizations, governments, companies to invest in payloads that could be flown on the shuttle. So my job on the shuttle program was to examine the capabilities that that vehicle could fulfill. Much as on Apollo, I'd been looking to stretch and advance the capabilities of the existing hardware. I was doing a similar job. So there's a lineage there as to logical flow with the shuttle.
Now, when it first started launching, it was considered a huge success. For the first time, we had something that was a reusable design that wasn't just wasted post-launch as with Saturn V launcher. But after Challenger and Columbia, questions were obviously made about its design. And I've heard and interviewed the first woman to command the space shuttle, Eileen Collins, say it was a bad design. Do you believe that, with your engineering hat on?
Yes, I think it was a very bad design, and I think that became apparent long before it began flying. It was designed down to a congressional limit on the amount of money we could spend each year and in total on the shuttle program. It came in at the end closer to the budget estimate. It was still over budget when it was completed in its development phase. But it was flawed. We promised too much to too many. In order to get the Air Force on board, the huge payload capability was to satisfy a military requirement for spy satellites that were to have been launched on the shuttle. It had huge cross range because the Air Force wanted to be able to go up and come down within one orbit and deploy a satellite before the payload could be tracked by Russian radar stations. That required a huge wing area. That drove up the amount of pressure on the thermal insulation. That put us toward tiles and the vulnerability that brought down both Challenger and Columbia. But certainly right from the very first flight, looking back, that was arguably the most pressing bullet that we dodged on that first flight, because now retrospectively applying the rationales for risk analysis and failure propagation, looking at the system now, the first flight had only a 50-50 chance of getting the crew back alive, and yet at the time it was believed to have a 99.99%.
Wow. One of my regrets is that I never saw a shuttle launch. I've seen other launches, but not the space shuttle, either launch or land. Did you ever get to see one yourself?
Oh yes, I used to take people down from the business community in London and Wall Street who were backing commercial payloads, bankers, insurance people. We'd brief them at Cocoa Beach in the Crossways Motel the night before the flight, because a lot of these people didn't know which end was up and which went front, the pointed or the blunt end. Bless them, and they were going to be investing millions in the payload, so we needed to brief them. And so I took quite a number of those groups to the Kennedy Space Center. We got VIP tickets for them, saw quite a lot of shuttle launches, and they were very, very different to the Saturn V.
Good though.
Very good.
Now, today we're talking about going back to the moon. NASA's made its pledge, going back to the moon, to put footsteps on the moon by 2024, including the first woman. There are plans around the world for a moon base. Do you think it's as big an engineering leap now to go back, considering the technology has totally changed, as it was in the 60s?
It's certainly not a leap of any kind. It's merely an application of existing capabilities, none of which really come out of the Apollo program, because as an engineering study, the Apollo program was a closed-loop solution to an open-ended challenge. And what that means is that the solutions that solved the problems in getting to the moon the first time were of their time and for their time, but the consistency of space technology development to date, through the International Space Station, through the burgeoning commercial environment as well of space rockets and satellites, an application of those capabilities is the way that we will go back to the moon.
Well, NASA has always seen the return to the moon in more recent times as a stepping stone to Mars. So it seemed an appropriate time for me to go and meet Abbie Hutty. She's an engineer at Airbus Defence and Space in Stevenage in the UK, and they have their very own Mars yard, which is where Abbie has been instrumental as an engineer building Europe's first rover that is going to Mars on the ExoMars mission next year.
This is our Mars analogous terrain. It's a warehouse full of sand and rocks. We've got the right colour of lighting for Mars, for a Martian day, and there's a backdrop all around the edges which is actually a panorama from Mars taken by Curiosity, so it gives you a really good idea of what the actual terrain on Mars looks like. And we've picked the the sand to be the right kind of colour to match that.
And it's a sort of terracotta brown.
Yes, it's all about making it look like Mars, specifically so that we can develop our autonomy systems. And that means we have to have something that looks like Mars so that the cameras get realistic kind of terrains and contrasts and images to then be able to do their algorithms on those and calculate our routes through.
And which is why these rocks actually do look very similar in shape and size to the ones in the panorama, so that your rover, which we'll go over to in a moment, I can't wait to go over to meet it, will navigate its terrain.
Absolutely. We know roughly what the size of obstacles and rocks and their composition and likely shapes are on Mars, so we've picked them to be among the most challenging that we're likely to experience as we're driving around on Mars. We need to know that there's some that are going to be too big for our rover to drive straight over, and it has to be able to recognise that and drive around them accordingly. So we need some that are navigable, some that are slightly outside of its capabilities, so that we can make sure that it makes the right decisions as it's doing that driving through the terrain.
Now, I know that you have several prototypes of the ExoMars rover. This one is a predominantly silver one, a bare one. It hasn't got effectively, if it was a car, you're just looking at the chassis effectively.
So this one's Brian. It's our current most realistic autonomous navigation prototype, and that means that we've got the right cameras on board so that we get the right images in. It's got the right processors to do the algorithms and calculate the path that we need to drive, and it's got all of the right wheels, locomotion system and actuators so that we can actually perform that drive, that manoeuvre that we've calculated. Everything else isn't representative of the rover. So one of the big things that we have differently here in our Mars yard is that we have much more gravity than there is on Mars. Mars is smaller than Earth. It only has about 0.38 of the gravity of Earth. So to make our rover sink in sand and slide down slopes and all of those kind of things in a representative way, we have the rover that only weighs 0.38 of the mass of the flight rover.
Ah, clever. Well, shall we walk up into it? I think both of us are wearing sandals, so I'm sinking into the sand. It is just like being on the beach.
It is exactly like being on the beach, yep. This is Brian. So up close you can see we've got the flexible wheels, the 6 flexible wheels, and they're fully metallic. And that's because we don't want to contaminate Mars with Earth life, and rubber tyres come from trees, so we don't want to have rubber tyres, but we still need to get that kind of flexibility in our wheels to get the kind of traction and grip climbing over rocks. So we've come up with these spring wheels that actually provide all of that with a metal wheel. You've got each of your 6 wheels is joined to another, so on pairs, and they're on a rocker system which actually keeps all of the wheels in contact with the ground no matter what terrain you're driving over. And then you can see that we've got this tall mast on the top which has the cameras at the top, which is how we see where we're going to drive effectively. So you need a little bit more height to be able to see a good distance over kind of dunes or craters or rocks or whatever it is, and make sure that you're going to be able to navigate from those.
Let's get it started then. Better explain that little tinny sound are the grains of sand sort of hitting the inside of the wheels as it flies off.
Yeah, because it's an electric vehicle, the motors themselves are really quite quiet, so we can't really hear any kind of engine running or anything like that. But actually, yes, as you drive across the sand, you get these little pings as the sand grains flick out of the wheels, because they do compress and they squeeze those sand grains out. So you get this interesting kind of crackling noise from the rover.
Now, how challenging an engineering project has this been for you? And you've gone through several roles as an engineer through the whole process of this rover.
The thing that I've really loved about working on the rover is that nothing is straightforward, nothing is normal. There is no normal. It's a Mars rover. It's the first time that Europe's ever built a Mars rover, so you have to really start from a blank sheet of paper and just see what will work. So there's been a lot of trial and error. There's been a lot of things that we've tested and then found that they didn't work as we'd hoped that they would, and we've had to take alternative paths. So there's been a lot of lateral thinking, and there's been a lot of brainstorming and going back to the drawing board, and a lot of learning about Mars, which I never thought I'd have to do. So we've had to learn about whether the dust storms would erode the surface of our structure, and the temperature fluctuations on Mars, and all of these really interesting things, just to make sure that the solution that we come up with will work for this other planet.
And that's sort of what an engineer does, though, isn't it? Is nothing is ever as planned normally, that you have to work things out.
Well, yeah, engineering a lot of the time is about trial and error, and it's about incrementally improving things and trying one solution and then modifying that solution and evolving that solution until you come up with something that works for all situations as you designed it.
And was there any particular aspect of this that you are most proud of, or that you think that as an engineering, even if it's a tiny small bit of it, that you thought, yeah, that was good, or yeah, I'm really proud of that?
I really enjoyed, I was the structures engineering team, so it's going to be the first carbon fibre structure of a Mars rover, which, to be able to say that I've helped design the first carbon fibre vehicle on Mars, that's pretty cool. So yes, the chassis that's a bit like a Formula One racing car, the kind of carbon fibre monocoques that they have, it's that kind of construction process. And then just some of the bracketry that we've had to put onto the rover. I mean, it doesn't sound very exciting if you're not a mechanical engineer, but having to build something that will have flexibility as you go through the day to night temperature ranges, because you get that expansion and contraction, you have to absorb that, but then it still has to carry the high loads through the launches and the landing, and then you have to drive over rocks, and you have to have enough stiffness to be able to withstand all of the forces there. We've come up with some very exotic titanium machinings which they've come in and they just look beautiful. They're works of art, and that's not because we've made them beautiful out of any aesthetic kind of reason, but actually because that's the way that the laws of physics have required us to do it. But I really love that combination of beauty and functionality that you get through something that has had to be pushed to the extremes like this.
Could you see yourself and Airbus designing a lunar rover at some stage in the future, particularly with everybody wanting to return to the moon?
Absolutely, and I think there's a lot of the technology on this rover that would be transferable to that kind of a project. You have many of the same challenges on the moon. You've still got issues with dust and whether that gets into your motors, how sharp the dust can be, and whether that damages parts of your structure or parts of your mechanisms. You've got very cold temperatures because there's effectively no atmosphere on the moon, where
it's gone over a bit of a
bump
there on one of the rocks, yeah.
And all of the same autonomous navigation systems could be applied equally well on the moon. So I'd love to work on a lunar rover. I think that would be a great next challenge.
So what are your final stages then for this rover before it goes to Mars?
So we're building the actual flight rover at the moment in our clean rooms here in Stevenage. We're coming to the end of the build now. Very nearly everything is together. So once everything is finally integrated together onto the rover, that goes out to France, and we do what we call environmental testing. So that's things like making sure it will survive the acoustic pressures during launch, the extreme temperatures on Mars, and then we do some communications testing as well to make sure that all of the functionality of the rover is working as expected. And then that's it really for us. We deliver it on and it gets integrated into the descent module, which is the thing that gets it down from Mars orbit to the surface of Mars, and that gets integrated into the cruise module, which is the thing that gets it from Earth orbit across to Mars orbit, and then it gets integrated into the rocket, which is the thing that gets it up into space in the first place. So all of those integrations take a little bit of time. It's due to launch in August of next year, 2020, so that's where we are heading towards with all of our integrations at the moment.
Abbie Hutty there. David, what's different, do you think, between getting us to the moon and getting to Mars, apart from the distance?
Survival. We have not yet been able to demonstrate the ability to keep people alive outside the Earth's magnetosphere for any longer period than about 8 or 9 days. And I think, as well as the engineering challenges, I think the biophysiological problems that we know we will face have to be evaluated first at a gateway station around the moon, at permanent bases on the lunar surface, where for most of the time they will be living in the full exposure of the solar wind and of cosmic radiation, cosmic rays, which of course are deflected and deterred by the magnetosphere. That's a great unsolved area, and while there's good PR, we're really not yet tackling that as not so much an engineering challenge, because I think those are the challenges of going from here to Mars are less than those we face than going to the moon with Apollo. But I think the biophysiological challenges are going to be immense, and we'd better be prepared for those.
You're right, and as many people pointed out with Andy Weir's magnificent book The Martian, which was later turned into a film, the main aspect, if that was done totally without creative license, The Martian would be dead from radiation.
Yes, indeed. Yes.
Now, we have some questions on Twitter. Here we go. Jeffrey Matthews wants to know, you might not know this, of course, whatever happened to the documentation for the Saturn V IMU? The software is lost.
Well, I'm not so sure that it is lost.
Oh.
There were 4 computers that were provided for the Apollo program, and it was the Saturn V computer which was arguably the most important. It was, after all, the one computer, or the one computer system, which saved Apollo 12 when all of the systems on the Commander Service Module went out after it was struck by lightning. I'm not aware that the software for that is lost. I certainly have all the computer books and the code books for the Apollo guidance computer, and that's one that is open-ended for me, because I didn't think it was lost. So,
well, that's good. Maybe we'll find out. Also have a question from Libby Jackson, who works at the UK Space Agency. What was the best or the most satisfying problem you personally had to solve?
I think the fact that tasked with stretching a vehicle that was designed to spend 30 hours on the moon, making it capable of spending theoretically up to 80 hours on the moon, in demonstrating that you can build in intrinsically to a system that is spearing for a single particular purpose, a capability that will allow one to extend it beyond its reach. And that's what we did with the Apollo hardware, with the Commander Service Module and with the Lunar Module.
Another one from John Terces. Would you like to see the Apollo moon landing sites preserved untouched, or recover components to learn how they've lasted 50 years in space? That's quite an interesting one.
Yes, that's a very interesting question. I would like to have them preserved. I think that is a very important set of iconic representations of those great achievements at the dawn of the space age. I think as well there is great good purpose to retrieving samples were retrieved of the Surveyor 3 by Apollo 12 that had been on the moon for just 2.5 years. But for 50 and more years, I think the forensic separation of certain pieces of equipment, but then to leave them alone and respected as iconic sites for what we can achieve if we put our minds to it.
I would quite like to go back to Beagle 2 and find out why one of its solar arrays didn't open. That would be very interesting, wouldn't it? Now, we've got Amanda Groombridge as well. If Apollo 10 had landed on the moon, would they ever have been able to leave due to the amount of fuel versus the module weight?
No, they would not, because of course it was carried only the propellant, the fuel and the oxidizer, which was sufficient to get back up into orbit, and it could not fire its engine for the 7 minutes that it would coming up from the surface. So the weight it had when getting back to the mothership would have been far too heavy compared to the offloaded, discounted propellant it had, just going down and then using a small propulsive burn to get back up again.
And David Payne, what was the most bizarre source of inspiration in solving an Apollo engineering problem that you are aware of?
Well, I think one of the most bizarre and one of the most simplest, which brings you down to earth, if it's not an oxymoron, talking about rocket launches and moon flights, was the fact that a number of us had to go to the top of a Saturn V, lie on our backs on mattresses, feet against the sides of the rocket stage, and rock the thing back and forwards, just to prove that all the integrated strain gauges were in place and recording that we were actually trying to kick a Saturn V over.
Please don't do this at home. I think that's a great one. Well, that's a brilliant place to end there for our episode of Create the Future. Thank you once again to those people who tweeted in some questions there, and a huge big thank you to David Baker.
Thank you, it's been a pleasure.
And Abbie Hutty. Join us again next month on the Create the Future podcast.